Welcome to this video on an introduction to electromagnetic waves. In this video, we're going to take a look at the broad category of wave phenomena in general and specify how electromagnetic waves are different from other kinds of waves. And then in the next several videos, we'll take a deep dive into each of the different phenomena and look at ways that we manipulate them in our technology. So the first and most important thing is to think of an example such as this. So over here I have an antenna, and this antenna is producing what I'm going to refer to as an emitted wave. So this emitted wave is going to be called more specifically a radio wave. And somewhere in someone's house, in someone's room, far away is an ear. And this ear is going to experience what I'm going to refer to as a received wave. And I'm going to refer to this wave as a sound wave. Now the thing is that you as the person listening are not actually hearing the radio wave directly. You can't hear a radio wave. Our ears are not evolutionarily adapted to be able to detect such kinds of waves. Our eyes, however, are, and we'll talk about that a little bit later. So what the heck's happening here? Well, the kind of wave that a radio wave is known as an electromagnetic wave, or an EM wave, whereas the kind of wave that our ears can receive, a sound wave, is known as a mechanical wave. And the major difference between electromagnetic waves and mechanical waves are how the waves are produced. Now, a lot of people will say that the major difference is that mechanical waves require a medium. So we can make a note of that because it is actually quite important. These require a medium, but it's actually not the most important distinguishing factor between the two. So these require a medium, these do not require a medium. Now, the required medium is the material through which the wave travels. So when we refer to a medium, we're really referring to not the size of a shirt, but the material or the matter through which the wave travels. Now, a wave can be referred to as a disturbance. Now, a disturbance is sometimes used to describe mechanical waves because this is some kind of energy that is disturbing a medium. But if electromagnetic waves do not require a medium, then how can they be a disturbance? Well, probably not the best way to describe them then. And that's something that we're going to take a look at in this video and several others following. So then how do you hear the radio wave? Because I'm pretty sure I've heard music playing. Well, it's actually being converted through this device, our stereo over here. So here's another antenna. You can see they kind of look the same, but this is going to be the receiver. And the receiving antenna is going to take the electromagnetic wave, specifically in the category of radio waves. It's going to receive this EM wave, and it's going to convert that EM wave into a mechanical wave. Now this occurs through the circuitry and the speakers, and in a later video I'll show you a cool project that you can actually build your own speaker. So there's some sort of conversion happening here between the EM wave and the mechanical wave. And the way that it's converted actually fundamentally shows the difference between the electromagnetic wave and the mechanical wave. So I said the EM wave does not require medium, the mechanical wave does, and that is a good distinguishing point. But like I said before, the most important thing is the production of these waves in how they are distinguished between one another. So let's take a look at what that means. So over here I have an electron, and this electron is at rest. Now we know, if you've been following the electromagnetism videos, that an electron produces an electric field around it. Now an electric field is kind of a generic term, but this electric field basically is representing the space around this particle and how it affects other charged things. So by merely having a charge, we have produced an electric field. Now we know in the magnetism videos that as soon as this charge starts to oscillate or move in any way, so as soon as there's a velocity of some kind, then there's also going to be a magnetic field produced. And what James Clerk Maxwell found was that when one is moving, it produces the other in sort of almost self-perpetuating way. Now, it's not energy that's coming from nothing because something had to get the electron moving in the first place. So the energy is coming from somewhere. But what ends up happening is that we get this electric field that is oscillating in one direction, and we'll talk about why we're using this shape here in a second. And then there's a magnetic field that's oscillating in the opposite or a perpendicular direction. So this would be coming out of the screen and going into the screen, and for lack of a better image, this is what I have. So when an electron moves, it creates an electromagnetic wave. Now, it turned out that all these electromagnetic waves that are produced can travel without a medium. So that idea comes back again, and we would say without a medium, this wave can propagate through space. So it's energy in some form that's traveling through nothingness. Now, can it also travel through other kinds of materials? Yes and no. And we're going to get to that in a minute. Now, a mechanical wave does something similar to this, but this is where we have a mass particle or a matter particle, and this matter particle is being disturbed in some direction, and because it's connected to another particle, the next little mass particle is then going to get pulled, and so on and so on. So here, there is some sort of disturbance, but the disturbance is traveling and disturbing particles so that the wave signal can travel from point A over here to point B over here without this actual particle making the move. Now, it's very important to note that this little electron over here that oscillated is not actually moving along with the wave. The mere fact that it's oscillating here in place, it produces a wave that then is left to go off on its own. Here you can see why you would require material all the way through the transmission of the wave. Because if all of a sudden there was a big gap, the wave or the disturbance wouldn't be able to affect the next particle. Now, we have two main categories of wave shapes, and we're going to refer to those as transverse waves and then also longitudinal waves. Now, a longitudinal wave is a sound wave, and longitudinal waves are really areas of compression and non-compression. So compression, non-compression. We sometimes refer to this as a pressure wave. This means that the wave is oscillating in the same direction as the wave propagation. So if the wave is moving left to right, the particles are moving left to right as well. A transverse wave is the more traditional shape of a wave where we have this up and down motion. Now, can a mechanical wave be transverse? Yes, it can. It can be transverse or longitudinal. But an electromagnetic wave is really only described as a transverse wave. Now, can you construct an electromagnetic wave by making longitudinal wave signals? Yes and no. There are many different overlaps of waves that we will talk about a little bit later, and so they can be made in different ways. But a main distinguishing factor is that a sound wave, which is a kind of pressure or mechanical wave, has little compressions, so the compression's moving through the air like this, whereas in this case we have some sort of oscillation back and forth and up and down. So waves have a set of properties that particles in general don't really exhibit, Or in other words, some of the things that we've observed when we observe waves are not the same things as what we observe when we observe particles. It's a lot more complicated than that, and we're going to get into it a little bit later. But let's just take a look here at a few different properties. Waves can reflect. So over here, this signal could bounce off this wall and echo back at us. We'd be able to hear ourselves if we yelled at this cliff face. Another very important one is refraction. This is the bending of a wave as it enters a new medium. So here we're going from air into water, and we can see there's some sort of bend in the wave. Here the wave is specifically light. Diffraction. Why do I have a tree here? Well, have you ever thought if someone hides behind a tree and they start calling your name to come find them, why can you hear them, which is a kind of wave, but you can't see them through the trees, so to speak? Well, that's because waves can actually bend around different objects and pass through openings in objects. But it has a lot to do with the kind of wave and also the material that is being encountered. So that's just a general discussion. Waves can also be polarized. If you think of sunglasses, if you buy polarizing lenses, they can help filter out, in a sense, a lot of light. Also, on the front windshield of your car, there are films that are added so that light reflecting from the car doesn't blind other drivers. And finally, one of the coolest, interference. If you've ever seen these weird soap films on bubbles creating all these really cool colors and swirls, that's an example of what we refer to as thin film interference. If you have noise canceling headphones, you've also heard of destructive interference, where it cancels out some sort of sound and is created by the idea of interference. So you can see here that waves have some properties that are really hard to explain from the particle models that we've come up with so far. And so what we're going to do in the next several videos is explore each of these in turn and take a look at how they can be manipulated to produce different kinds of technology.